C is the initial value, A is the base. Good. And then your variable is in the exponent. Good. So the growth of this function is all real numbers. This is the growth factor, and C is the initial value that's being multiplied by that growth factor. Okay. Why would we need these equations? Why would we need to work with these equations? Because if you happen to encounter X in the variable, you wouldn't, or sorry, X in the variable in the exponent, the X in the exponent, such as, I think we'll see this later, but 2X is 8, right? If it was 2 times X is 8, right? We know how to undo multiplication, we divide, right? We know how to do 2 plus X is 8, right? To undo addition, we subtract, right? We could even do the square root of X squared is 8, right? Because we know how to undo the square with the square root. We could even say, yeah, right? You undo what is being done to it. But I don't know how to undo a base if I am in the exponent, if the variable I want to solve for is in the exponent, right? So if I thought about 2 to the power of something is 8, right? 2 times something is 8, that something is 4. 2 plus something is 8, that is a 6, right? But 2 to the power of something is 8. I could just say, I don't know, what's, right? What's 2 to the power of 2? That's only 4. What's 2 to the power of 3? Oh, that's 8. Okay, I found it. X is 8. Or sorry, X is 3, right? So in this case, X is 3 because 2 to the third is 8. However, what if it was 2 to the X is 5? Yeah. Is X 3? It is not, right? 2 to the power of X equals 5. X is not 3, right? Is it 2? No, because 2 to the power of 3 is 8, right? 2 to the power of 2 is 4. So it's some number between 2 and 3, but we don't know where exactly, right? So today we're going to talk about how to find X if X is in the position of the exponent and it's not a perfect answer, okay? So let's talk about what it means when we have an exponent of X, okay? It means that you're growing exponentially. You are growing very quickly, right? You're growing at a rate that means that every answer, every time we increase this by a whole number, we grow that number of times our base, right? We grow our base that number of times. So this is a graph of exponential growth, a to the power of X, if a is bigger than 1, okay? If a is less than 1, but more than 0, it's exponential decay, and it's going the other direction. It's going down, okay? So if you look at your graph, you see it's going up from left to right. It is growing, and it is growing by a factor of a, your base. That's how fast it is growing. Each time that you increase x by a whole number, you multiply that a times itself again, right? So the characteristics of a graph of exponential growth are that the domain is the set of all real numbers between negative infinity and infinity. The range, right? The domain is all real numbers because it goes forever in this direction, forever in this direction, forever to the left and forever to the right on the x-axis. The range is the set of all positive real numbers. So it's not going forever in both directions on y, it's approaching 0 and never reaching 0, okay? And then it's going forever in the positive direction, so we call the range from 0 to infinity. We see that there are no x-intercepts. It will never cross the x-axis. That's why this is 0. And the y-intercept is always 1. So you will always have the point 0, 1 on the graph of exponential growth if it's not transformed in any way, because no matter what a is, if you raise something to the power of 0, the answer is always 1, right? Okay. The x-axis is a horizontal asymptote. If you look to the left, we approach 0, we never reach 0, okay, on the y-axis. And the graph of f of x is an increasing function and is 1 to 1. So increasing just means this, right? It's rising, it's growing, it's going up. It is 1 to 1. We talked about 1 to 1 on Monday. It means if I perform the horizontal line test, it only ever crosses the graph at a single point. It looks like it becomes flat down here, but it's just becoming the rate that it moves down is just growing slower and slower, but it's never a straight flat line. Every single point on y is unique. Good. So those are the characteristics of exponential growth, and very similar to exponential decay. The difference between exponential growth and exponential decay is a whole number, or sorry, a number greater than 1, then it's growth. If a is between 0 and 1, it's decay. It's going down. Oops, sorry, couldn't see that. Like that, okay? So we are asked to graph the exponential function f of x equals 3x, okay? I know about its attributes. I know that domain is all real numbers. The range is all positive numbers. There's not going to be an x-intercept. I know it's going to go through 0, 1, and that it will be smooth and continuous, right? But I don't know enough to graph it, right? Based on those characteristics. I just have an idea of what it is supposed to look like. So to graph something, we can just create a table of values. Oh, okay, I want to start over because I know it's never going to go below that line, right? So I'd rather give it a little bit more space above that line. I know it's growing this way because 3 is greater than 1, right? If a is greater than 1, it's growing. Good. I know it's going to go through the point 0, 1. So this is the graph of f of x is 3 to the power of x. It's going to go through the point 0, 1, right? If I don't know anything else about it, I can just make a table of values like we've done before. What is x? What does f of x become for that x value? And therefore, what is my ordered pair, right? So I know that when x is 0, f of x is 3 to the power of 0, which is 1, right? So my ordered pair is 0, 1. We can also go, what is it when x is 1? Then we have 3 to the power of 1 is 3. So my ordered pair is just 1, 3, right? What about 2? That means I'm taking that original base and I'm raising it to the power of 2. 3 to the power of 2 is 9, right? So that's the point, 2, 9. So I can graph those. I have 0, 1, 1, 3, 2, 9. So you can see it's getting very steep, right? But it's never going to touch 0. So here it's going to become very, 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 very shallow. Good. Let's do a couple negatives just so we know what the graph looks like. So if I put a -1, what happens when I take 3 and I give it an exponent of -1? If you remember, to make an exponent that is negative positive, we put it across the fraction bar. So 3 to the power of -1 is 1 over 3 to the power of 1, which is just 1 over 3, right? So 3 to the power of -1 is 1/3. So that point is going to be -1, 1/3. Power to go to -2, right? It's the same. So 3 to the power of -2 is the same as 1 over 3 to the power of regular 2, positive 2, which is 9, right? So -2 is going to become 1/9, and it just gets closer and closer to 0 because it keeps cutting itself, right? But it's never going to touch 0. It's just going to become smaller and smaller and smaller, infinitely smaller. So -1 was 1/3. Yeesh. But -2 is already at 1/9. So you can see. That's it, right? The base is greater than 1. It's exponential growth. There's no y-intercept. Or sorry, there's no x-intercept. The y-intercept is always going to be at that point, 0, 1. Good. And it's smooth. It's continuous. So that is a graph of exponential growth. Now, same thing, f of x equals a to the power of x. However, a is now a fraction or a decimal that is between 0 and 1, okay? So this is exponential decay. You can see by the picture of the graph that instead of going up from left to right, it's going down from left to right, right? Falling rather than rising because the base is between 0 and 1. So the domain is the set of all real numbers. Nothing is excluded. There's never going to be a variable in a denominator. There's never going to be a variable under a radical, right? The range is the set of positive real numbers. Again, it's not going to touch the x-axis. It's always going to be slightly above the x-axis forever, right? It'll always have a positive y value. There are no x-intercepts. The y-intercept is 1 because even if it's a fraction, if it's raised to 0, the answer is going to be 1. The x-axis is a horizontal asymptote. It's never going to touch it. And it's a decreasing function. It's still 1 to 1. So it's basically just a flip of exponential growth, right? It has many of the same attributes. It's smooth and continuous. So instead of 3 to the power of x, let's graph 1/3 to the power of x, shall we? My base is now between 0 and 1. So that means most growth, the fastest growth, I should say. The biggest change is going to be coming on this side. And it's never going to go below this x-axis. Good. And that is because 1/3 is greater than 0, but less than 1, right? Right. We know that it always contains the point 0, 1. And we can make a table of values. This will be x, this will be f of x, and this will be my coordinate pair. Just use that and use that. So if x is 0, I know that f of x is going to be 1/3 to the power of 0. Even if it's a fraction, anything to the power of 0 is 1. So it's just the point 0, 1. Good. If it's the number 1, taking 1/3 times itself one time is going to give me 1/3 again. Right? So when x is 1, y is going to be 1/3. If I take 1/3 and raise it to the second power, 1 to the second power is just 1, 3 to the second power is 9, right? So it's 1/9. So the next point is going to be 2 1/9, and it's looking like the other one, right? It looks like we just flipped over that other graph because we're kind of just switching the negative and positive points, right? The negative one on the growth, exponential growth graph, the negative one was at 1/3, and the -2 was at 1/9. If we were to do -1, so 1/3 to the power of -1 means I take that 3 to the power of -1 and move it up here, and it's 3 to the power of +1, which is just 3. Good. So 1/3 to the power of -1 becomes a +3, no fraction, right? -2, 1/3 to the power of -2 means I'm taking that 3 to get that -2 to a positive. I want to move it up here. So that becomes 3 squared, which is 9. -2, 9 is my next point. So we have 0, 1, 1, negative, 1 1/3, sorry, no negatives. 1 1/3, 2 1/9, but -1 up to 3. Oh, sorry, it should be over here. -1 up to 3, -2 all the way up to 9. So you can see how fast it's falling in this case, right? Because we're always looking from left to right. So this one is falling like this. The other one was growing. So does it meet all of its criteria? It's decreasing. It has a y-intercept at 0, 1, and it's approaching y equals 0, but we'll never touch it, right? The rate of decay is 1/3. I'm dividing each number, each point, each time I move one whole x value, I'm dividing my answer by 3. So I'm just decreasing, and it's going to get 2/3 smaller each time, but it's never going to be 0, right? Because you can always divide a number by, if you're dividing a number by a number that's not 0, you're not going to get, you'll never reach 0, right? You'll just get a smaller and smaller number. Okay. Now, what if we had, instead of 3 to the power of x, it was 3 to the power of -x plus 1? That means we are transforming it, right? It's still an exponential function, a graph of an exponential function, right? And this is the graph of, we already graphed it today, y equals 3x, or that is the same as f of x equals 3x. Sorry, 3 to the power of x, I shouldn't call it that. So this is the graph of f of x equals 3 to the power of x, right? And then they're asking us to transform it. So you come back to the transformation rules for functions. If we look at what is happening to x and then what is happening to the entire function, right? Is it happening to x, or is it happening to all of f of x? And what does that mean, right? So let's review the transformation rules, right? If we're adding or subtracting, it's going up and down. If we're adding or subtracting within the exponent, then it would be translated left or right. If we make everything negative, we're reflecting it over the x-axis. If we make just the x negative, we're reflecting it over the y-axis. And if we multiply everything by a, we're stretching it or compressing it. If we're multiplying x by a, we're horizontally compressing or stretching it. Good. So those are the rules. So let's see what we have in this example. So definitely have your transformation rules for functions out to solve problems like this. We have a negative, just the x. We made just the x negative. So that looks like a reflection over the y-axis, right? So that is a reflection over the y-axis. Every x value becomes a negative x value, okay? Just trying to think of how best to write this. So the negative x becomes a transformation or reflection ignore that I wrote transformation. Reflection over y-axis. Good, and that's the y-axis. The negative x. There we go. Okay, that feels right. And so we worked from the outside in, inside out, sorry. From the inside out. Now we have +1, right? The +1 is outside. It's not right in the grouping symbol of the x, which would mean it was in the actual exponent. It's not in the actual exponent. So it would be a vertical translation. Because we're adding 1, it's a vertical translation up 1 unit. On the y-axis. Good. So that one means every y now becomes y +1, right? So down here, every x becomes a negative x and every y becomes a y +1. So if I have the point 2, 9, 2 is my x, 9 is my y, right? Then I'm adding 1 to 9, it's becoming 10. And I'm making my x negative. So that's a 10, and that's now a -2. Right? Or if it's easier, you can just do it like flip it, move it up 1. Or you can go point by point. So 2, 9 becomes -2, 10. 1, 3 becomes -1, right? 3, we add 1, we get 4. 0, 1 remains 0, but 1 becomes 2, right? Because we're adding 1. -1, 1/3 becomes +1. Becomes +1, 1 1/3. The -2 becomes a +2. The 1/9 becomes 1 1/9. And then you just graph that. Yeah. So -2, 10. Is right here. So instead of -2, 1/9, you have -2, 10. -1, or sorry, 1, 3 becomes -1, 4. 0, 1 becomes 0, 2. 1, -1, 1/3 becomes 1, 1 1/3. And so now, instead of approaching y equals 0, we're just approaching y equals 1. So I'm just going to kind of slowly shuffle it out there. And that is the transformation of 3x to 3 negative x plus 1, using the transformation rules for functions because these are still functions. Good. The parent function was f of x equals 3 to the power of x. We reflected it across the y and we shifted it up 1. The horizontal asymptote is now y equals 1, right? Instead of y equals 0. All right, that was example 3. The number e. The number e is defined as sorry, 1 second. All right, ready. The number e is defined as the limit as n approaches infinity of 1 plus 1 over n, but raised to the power of n. It has a numerical value just like pi in your calculator. So you can put e into your calculator and you'll get a number. It's this guy. So it's approximately 2.71828. Good. It comes up after college algebra. So if you wanted to graph f of x equals e to the power of x, you would need to calculate each value, each x value, each power, each number you can take e to the power of, right? So e squared is a button on your calculator. Or you can just say e raised to. Yeah. So you want to be able to do that. And know whether the graph of e is a graph of growth or decay, right? So just e of x is a table of growth, right? Because we can see it's going up from left to right. What is e? It's any, at any point in the graph of e to the power of x, the slope of e to the power of x is equal the value of e to the power of x. So when x is 0, e to the power of x equals 1, and the slope of e to the power of x equals 1. When x equals 1, e to the power of x equals e, and e to the power of x has a slope of e. And that's true for any value on this graph. That is the importance of the number e. You can just put it in your calculator. All right. So we can put e into our calculator. If we put e into our into a graphing calculator, it gives us this, right? It gives us these values. And what if we wanted to transform it? So if that is y equals e to the power of x, and we needed to transform it by making the e negative and adding 2 to the exponent, what would happen, right? So we can do it the same way we did it in the previous example, even though we have that e is a constant number. Okay, so it's not a number to be scared of. It sounds a bit complicated, but it's something we can work with the same way we work with a constant, any other number. Okay. So here's the graph of e to the power of x. The values are 2 for our x, and y becomes e to the power of 2, right? When x is 1, y becomes e. Just like everything, when x is 0, y is 1. And then when x is -1, the y value becomes 1 over e to the power of 1, right? Instead, we're going to take all of this and we're going to make it negative. That means we're reflecting it over the x-axis, right? Because the negative is out here, it's not up here with the x. And we've already learned this. So the e is being multiplied by a negative. When just the x was being multiplied by a negative, it reflected across the y-axis. But when everything's being multiplied by a negative, it's reflected over the x-axis. Good. So the negative is a reflection across the x-axis. And the +2, what does that mean? The +2 is inside the grouping symbol with the x, means it's a horizontal translation left 2 units. Good. So if we're reflecting across the x-axis, that means all of our y's become negative y's. So let's look at y. Here, y is e squared, right? So now it becomes e to the -2. Here it's e. Sorry, it's negative e squared. X. Yeah, all our y's become negative y's. So that is definitely not what we're doing. It's negative e squared, right? E becomes negative e. 1 over e becomes negative 1 over e. 1 over e squared becomes negative 1 over e squared. So I have made it reflect across the x-axis by changing all my y's to negatives or to their opposite, right? But they were all positive, so now they're all negative. And then I confusingly did that in the purple. Bah. Now we're translating it left 2 units. So left 2 units means we're subtracting 2 from every x. So instead of 2, that's going to be a 0. Instead of a 1, that's going to be a -1, right? Instead of a 0, that's going to be a -2. Instead of a -1 over, or sorry, instead of a -1, that's going to be a -3. Instead of a -2, that's going to be a -4. Good. So what it's going to look like is something more like that. Good. All right, so that's how to graph. And you can always check in Desmos that your graph is correct and compare it to the parent function. Now, the final thing, completely new concept, is how to solve an exponential equation using the rule of exponents. Okay, so new rule of exponential equations. If a to the power of u equals a to the power of v, then u equals v. It sounds believable, right? If your bases are equal, your exponents are equal. If you have an equation and the base on the left is equal to the base on the right, then the exponent on the left has to be equal to the exponent on the right, right? So we're going to solve 2 to the power of x plus 2 equals 8 using this rule, okay? Is there a way, here we have a base 2 with an exponent x plus 2, and on the other side we have a base 8 with an exponent of 1, right? Is there a way to make 2 and 8 into the same base? 8 is in fact, right? 2 times 2 times 2 is 8, right? So 8 is actually, as we talked about on page 1, 2 to the power of 3, right? So we can rewrite this as 2 to the power of x plus 2 equals 8. And instead we can say it's 2 to the power of x plus 2 equals 2 to the power of 3, so that you have the same base. Now on both the left and the right, we have a base of 2. If you have the same base, then you can say, oops, that those exponents are equal. Good. So my same base of 2 means that I can say x plus 2 is equal to 3. That means my x is 1, right? I can also check this with a calculator. We don't really need a calculator. 2 to the power of 1 plus 2 is 8. Good. Or you could even say 2 to the power of 1 plus 2 is the same as 2 to the power of 3. Also true. 9 to the power of 2x minus 5 is the same as 27 to the power of x, right? Here, we manipulated this side of the equation, so it matches the 2, right? We wanted the 8 to match the 2 because 8 was and it worked because 8 was a multiple of 2. However, we can't do that here, right? 27 is not a multiple of 9. 9 to the power of 1 is just 9. 9 to the power of 2 jumps to 81, right? But we can check and say, can I change, is 9 a perfect square? Can I change 9 into something that is an exponent? We can, right? 9 is the same as 3 squared. Right? Instead of saying 9 to the power of 2x minus 5, we can say 3 to the power of 2 times 2x minus 5. Good. And 27 is 3 to the power of 3, right? 3 to the power of 2 is 9. 3 to the power of 3 is 27. So that becomes 3 squared to the power of 2x minus 5 equals 3 cubed to the power of x. Good. Now we're just multiplying exponents. We're raising this 2 to the power of 2x minus 5. So following the rule of exponents, we're going to multiply that 2 times 2x minus 5. Good. And here we're going to take that 3, the second 3, the exponent 3, and multiply it by x. So what we're going to get is 3 to the power of, distribute the 2, 2 times 2x is 4x. 2 times negative 5 is a negative 10. Oops. 3 to the power of 3x. Good. Now that our bases are the same and our exponents have been simplified as much as possible, we can say that because the 2 is equal to 2, the x plus 2 is equal to 3. Here, the 3 is equal to the 3, so we can say the 4x minus 10 is equal to the 3x, and we can solve for x. Good? All right. Go ahead. I'll just move the, I'm going to move the 3x, so I don't have a bunch of negatives. It's one extra step, but there's no negatives. So 4x minus 3x is just x minus 10. There's nothing over here now. So x minus 10 equals 0. Add 10, both sides, and you get x is 10. Now you can check that is 2 times 10 minus 5 would be 15, right? Is 9 to the power of 15 the same as 27 to the power of 10? So does 27 to the power of 10 equal 9 to the power of 15? How you would check it. Yeah, there you go. All right, and here's e. E to the power of negative x to the power of 2 is equal to e to the power of 5x times 1 over e to the power of 6. Good? All right, so let's simplify. Oh, sorry, I'm not even showing you what we're on anymore. All right. E negative x to the power of 2 equals e 5x times 1 over e to the 6th, right? So that I have plenty of space. Okay, let's simplify this as much as we can. We obviously don't have all, we have all the same bases, but this one's a fraction. So let's fix it, right? Let's change, since this is a multiplication and I want to multiply this by this fraction, let's turn this into a fraction and multiply it straight across. Okay, so now I have e to the power of 5x over 1 times 1 over e to the power of 6. That just becomes e to the power of 5x over e to the power of 6. Good. Negative x squared, e to the power of negative x squared is equal to e to the power of 5x over e to the power of 6. Good. Now, I want to divide this so that I only have one term, right? So this is e to the power of 5x divided by e to the power of 6. If I were just to rewrite that, that would become according to the rules of exponents, right? If the base is the same, I can subtract the exponents. I can't take 5x minus 6 and get one term, but I can write those two terms and just have one base, which is what I need to solve for x, right? I need one base. So we went from e to the power of 5x times 1 over e to the 6th. We multiplied those. We got e to the power of 5x over e to the power of 6. I know we're running out of time. And because I just want to find x, I changed that to 5x minus 6 and kept the base. Okay. Now I have the same base and I can say negative x squared equals 5x minus 6. Good. Now we're just going to, we have an x squared, we have an x, and we have a constant. So I'm going to put it into standard form. Yeah, and either solve it with the quadratic formula, or I can try to factor it, right? A is 1, C is negative 6, B is 5. So that'll be x times x, right? And I want it to multiply to negative 6, but add to 5. So I can just say it is x plus 6, x minus 1, right? My two answers are x is negative 6 and x is positive 1, right? So I know that was very complicated and required knowing, like remembering everything we've learned this semester to know exactly what to do for each step, because each step looks so a bit intimidating. But if you know what to do, you definitely have these skills. These are very easy. Okay.